So now we will discuss the AC power. So there are various kinds of power: average power, reactive power, complex and apparent power. So what are these different powers? In the DC circuits, we have talked about instantaneous power. So what was instantaneous power? This is P of T is equal to the voltage into current I of T, right? So we called it the instantaneous power, but since in DC circuits the values are constant, instantaneous power will be the same as normal power. But when we are dealing with AC powers, here they are time varying, okay? So we are no more interested in just the instantaneous power. We want something else. And that something else is the average power. So what is average power? This is the integration of the power over one time interval divided by T. Just the average, summing all of them and then dividing by the time, right? That is the definition of average. So this is the average power. So this is the meaning of average power. Next, another important term is the root mean square value. So this is abbreviated as RMS. So what does this mean? So first you can write the definition here. The RMS value of a periodic current is the DC value that delivers the same average power to a resistor as the periodic current. So we will see what it means. First, if you take a resistor, okay, now let us say a current I of T is flowing through this resistor R, okay. So this is case 1. Then what will be the average power that is delivered to this? This is equal to 1 by T, the time period of the periodic current, integration over the time period, I square of T into R dt, right? The instantaneous power is equal to I square into R. Now through the same resistor R, a DC current is flowing, let us say. Okay. Now what will be the power that is dissipated here? The power dissipated here is I square R. Okay. So now what is given in the definition here? The RMS value is the DC value that delivers the same average power as the periodic current. Okay. So that means if the average power and this power dissipated is equal, then this value of current is what we term as the RMS current. So that means if this we will take as P average. So if P average is equal to this we will take as P DC. P DC, then the DC value I is equal to the RMS value of the periodic current. Okay, so that is the definition. Now we will see what is the expression. Okay, so what is this value of I? We will write this as IRMS. Okay, so then what will we get here? IRMS square R. This is the power dissipated in the DC case, second case. So this should be equal to the average power, which is 1 by T integral 0 to T I square of T R dt. So R and R will get cancelled. Then what will be the value of IRMS? This is equal to the root of 1 by T integral 0 to T I square of T dt. Okay, so you can see that first the current function we are squaring, then we are taking the average, or we can also call it as mean. Over that we are taking the root. So root, mean and square. So this is the expression for the RMS value. Now this RMS value concept, it can be extended towards the voltage as well. So if you take any signal x of t, this is in general RMS value of x of t is given by root over 1 by t integral 0 to t x of t whole square dt. Now RMS value you can find out for various waveforms. It is particularly important to know the RMS value of sinusoidal waveform. Okay, so RMS of sinusoidal wave. So we will take the voltage or current. You can take either of the things. So V of t is equal to Vm cos omega t, let us say. Okay, so then what will be the RMS value of V of t? So this is equal to root over 1 by t integral 0 to t, and V square is Vm square cos square omega t d omega t. Okay, so we will differentiate with respect to d omega t. So this is going to be root over 1 by t integral 0 to t. Vm square you can take out common, so you're going to get Vm. Cos square omega t you can write as 1 plus cos 2 omega t divided by 2 d omega t. So this you're going to get Vm by root t into root over t minus 0 by 2 plus sine 2 omega t divided by 4 from 0 to t. Okay, so whenever you are integrating a sine function over its time period, okay, so this is the sine function. Now 0 to t is this. For sine 2t what will happen? The frequency is double. That means 2 cycles will be covered in the same time period. So it is going to be like this. So now 2 complete cycles are being completed. For such a case, if you take the average value, then you're going to get 0. Okay, so you can verify it as well. So this will become 0. So what you're going to get finally, here t and t will get cancelled. So the final RMS value is going to be Vm by root 2. So the maximum value, the peak value of the cos function divided by root 2. That is the RMS value. So you can write maximum value divided by root 2. Let us now see what is the average power for a sinusoidal voltage and current. So if you consider a circuit element through which a current I of t is flowing and the voltage across this is V of t. Okay, so V of t is equal to, we will take some Vm cos omega t plus theta v. Okay, the phase of the voltage we will take as theta v. Now the current I of t is equal to, you can take the maximum value as Im cos omega t plus theta I you can take. Okay, from here we can get what? The instantaneous power. Remember, this is the instantaneous power. This is equal to the voltage into the current, right? So the power at any instant of time t is equal to V of t, voltage at that time, into the current at that time. Okay, so what will you get? The instantaneous power Vm Im cos omega t plus theta v into cos omega t plus theta I. Now here you have cos into some function, into some argument, cos into some other argument. So you can write cos A cos B, and cos A cos B you can write as, using trigonometric identities, 1 by 2 cos A minus B plus cos A plus B. So we will apply this to this. Okay, so what are you going to get? Vm Im by 2 cos theta v minus theta I plus cos 2 omega t plus theta v plus theta I. What we did here, omega t plus theta v we took as A, omega t plus theta I we took as B. So A minus B, you're going to get omega t is cancelled, you're going to get theta v minus theta I. A plus B will be the sum of both of them. So you have this term here. Therefore, the instantaneous value of power you can write as P of t is equal to Vm Im by 2 cos theta v minus theta I plus Vm Im by 2 cos 2 omega t plus theta v plus theta I. Here you have a few observations that you can see. This term here, this is not dependent on time. Okay, so this is a constant. It is not varying with respect to time. Whereas this quantity here, it is a sinusoidally varying function. So it is time dependent. And also one more thing that you can see here is what is the frequency of this cosine function here. It is 2 times omega t. So that means if voltage and the current waveforms, they are having a time period like this, then the power waveform is going to have a time period of double. That means it will complete 2 cycles in the same time period. So you can write that point here as well. Frequency is doubled. Okay. So how will this look like? If you draw the graph of P of t with respect to t. Okay. So normally what will happen to a cosine function? It is going to be like this. Okay. So about this origin you will have the cosine wave. But now you have a constant value which is being added to it. So this wave will simply be shifted upwards. So if this is the new average value, Vm Im by 2 cos theta v minus theta I. So now the cos function is going to be starting from here. Okay. So now the average value of this function is going to be this DC value. So we will see that mathematically as well. Okay. So mathematically, here graphically we have seen that average power is equal to Vm Im by 2 cos theta v minus theta I. So we will see mathematically as well. How will you get? Mathematically, the average power is equal to 1 by t integral 0 to t, the instantaneous power you have to integrate. Okay. So what are the two terms that you have here? 0 to t Vm Im by 2 cos theta v minus theta I dt plus integral 0 to t Vm Im by 2 cos 2 omega t plus theta v plus theta I dt. Okay. So you can see that this is a constant term while this is a sinusoidally varying function. Now a sinusoidal function, if you are integrating over one time period, then what will happen? It will become 0. So this is becoming 0 because integration is over one time cycle. So only one term will be left out. That is the first term. So what are you going to get here? 1 by t into Vm Im by 2 cos theta v minus theta I. These are all constants, so you can take it out. So you're going to get t. Integration is only t result is. This is from 0 to t. So t and t will get cancelled. So what are you left with? Vm Im by 2 cos theta v minus theta I. Okay. So we can see that mathematically also we got the same result. Now this here it is in terms of the maximum values, right? Vm and Im. You can write in terms of the RMS values as well. So this you can write as Vm by root 2 into Im by root 2 cos theta v minus theta I, right? So what you're going to get? Vm by root 2 is V RMS, Im by 2 is I RMS into cos theta v minus theta I. This will be in terms of RMS values. So finally this is the expression for the average power. We will now see the average power for various circuit elements. So if you take first the resistor. So for a resistor, what is the phase relationship between the voltage and current? Both are in phase. Okay. I and V are in phase. So what it means? This means that theta V is equal to theta I, or theta V minus theta I is equal to 0. Okay. So this means that the average power P average is equal to V RMS into I RMS into cos 0. Okay. So cos 0 is simply 1. So you can remove this. So the P average is going to be simply equal to the product of the RMS values of voltage and current. This is only when the impedance is purely resistive. That means only R we are considering here. What about if we consider inductor L? Here what is going to happen? The current will lag the voltage by 90 degrees. So that means what will be theta V minus theta I? This is equal to 90 degrees. Since current lags voltage by 90 degrees. So what will you get? The P average you are going to get V RMS into I RMS into cos 90 degrees. So which is what? 0. So the average power that is consumed by the inductor is 0. So how is the average power coming to 0? This simply means that the cosine function or the sine function, it is oscillating over the x-axis. Okay. So the average value if you take it is 0. What happens is over one half cycle the power will be consumed by the inductor, and over the other half cycle the inductor will give back the power to the source. Okay. So that is why the average power comes out to 0. Similarly for a capacitor also the case is same only. Here the only difference is theta V minus theta I is equal to minus 90 degrees, because here the current leads the voltage by 90 degrees. Okay. Then the average power is once again equal to 0. So you can write the point here. L and C absorb power over one half cycle and deliver power over the other half cycle. Okay. So that is why on an average the power is going to be 0. But if you have a combination of R and L or C, let us say we have an RL circuit. In this case it is going to be, the average value is not going to be 0, but it is going to be instead V RMS I RMS cos theta V minus theta I. Depending on the values of R and L, you will have the phase difference anywhere between 0 to 90 degrees. Okay. So we have seen that the inductor and capacitor, they are taking 0 average power, but they are taking some power during one half cycle. Okay. Now what is the power that is being taken through that half cycle? We want to measure that. So why is that the case? Okay. So that is because of a term called power factor. So first we will see what is meant by power factor. So we saw that the instantaneous power in a DC circuit, the power was given by V into I. Okay. Now in AC circuit what is happening? The average power is given by V RMS into I RMS into some other function is coming here. What is that? Cos theta V minus theta I. Now this extra term is reducing this V RMS into I RMS, right? Because this term is always less than 1, right? Cos of something will always be less than 1. If you take the DC analogy, it should be only the product of the RMS values, because RMS values are the DC equivalents we have found out, right? So it should be the product, but it is being less than that by how much factor? By this much factor. Okay. So for that reason, this term we call it as the power factor. Okay. Fraction by which power is reducing. Now what is this depending on? This is depending on theta V and theta I. What is the phase difference between the voltage and current? Okay. So the phase difference will come into picture when only when L and C are present. If there is inductor only, then there is no phase difference. Okay, so that is why it is important to know about how much the L and C are affecting the power that could have been taken. Okay, so for that we need to make use of another power called as the reactive power. So this is given by Q. Also, in order to express both the real power or the average power and the reactive power, we make use of another quantity called as the complex power. Okay, so this is the complex power. So we will see what are the relations between all of these different kinds of powers. Since we know the expression for average power, we will start with the average power. So what is this? V RMS I RMS cos theta V minus theta I. Okay, this how you can write? You can write it as the real power of V RMS in the phasor form into I RMS conjugate in the phasor form. Okay, so what is V RMS here? Here V RMS phasor is nothing but it will have a magnitude of V RMS and angle will be theta V. And what about I RMS conjugate? This will have I RMS angle theta I. So what will be the conjugate? Conjugate will simply be equal to the same magnitude but negative angle. So why is that? Conjugate is actually coming from the real and imaginary terms. If you have a real complex number a plus jb, okay, then its conjugate will be a minus jb. So this, if you write in magnitude and phase form, it is going to be root over a square plus b square tan inverse b by a. This is the angle. What about this? The magnitude will remain same, root over a square plus b square, but angle will become minus tan inverse b by a. Okay, so conjugate, when it is in the magnitude and phase form, the only difference will come in the phase. The phase will become negative. Okay, so what we have here? V RMS I RMS conjugate. So what will it be if you multiply this and this? V RMS I RMS angle theta V minus theta I. Then what will be the real part of that? Cos theta V minus theta I. Okay, so this is how we are representing the average power. This is called as the average power or also the real power. Now this term that we have here, this we take it as the complex power. Okay, so the complex power S is given by V phasor and I phasor, which is in the conjugate form. Okay, so we have defined the complex power. So the real part of complex power is equal to the average power, and the imaginary part is going to be equal to the reactive power. Okay, so you can write the real part of S is equal to V RMS I RMS. Phasor will be usually in the form of the RMS value unless otherwise mentioned. Okay, cos theta V minus theta I. So this we write as P. Then what about the imaginary part of S? So this is going to be V RMS I RMS sin theta V minus theta I. So this is equal to, this is represented by Q. So this is the real or average power, and Q is called as the reactive power or the imaginary power. Okay, so we often make use of reactive power term only. Okay, so S you can write as P plus JQ. Okay, now what about the units? We know that the unit of the average power, this is anyways in watts, and the symbol is W. Now what about the complex power? In complex power you have the units as volt ampere, VA. Okay, because it is simply the product of voltage and the current. So to differentiate from the P, we write as voltage ampere. Okay, then what about the reactive power? This is given as volt ampere reactive. Okay, because all of these powers, they are the product of voltage and current only, but there is a slight difference. So to differentiate that, we call it as volt ampere reactive, which is abbreviated as VAR. VARs also sometimes we call it. So what are all the points that we have learnt here? The first point we learnt is S bar is equal to V bar I bar conjugate, and the second point is to express the P and Q in terms of the real and imaginary parts of S. So that finally complex power we can write as P plus JQ. Then we also saw the units of each of the functions. Okay. Now the next point that you need to know is how the value of reactive power varies with each load. Okay. So reactive power Q is equal to, for resistive loads, for purely resistive loads, theta V is equal to theta I, right? So in that case, sin theta V minus sin theta I is 0, right? So reactive power is equal to 0 for purely resistive loads. This is because for purely resistive loads, theta V is equal to theta I, making sin theta V minus theta I is equal to 0. Okay. Then what about for inductive loads? For inductive loads, Q will be greater than 0. So inductive means the inductive load is dominating. It is having a dominant effect. So this means that it can be simply R plus J XL or R plus J XL minus XC, where XL is greater than XC. Okay. In either of the cases, we call them as inductive loads. So what will happen in inductive loads? Here theta V will be greater than theta I. For inductive loads, current will always be lagging the voltage. So that is, for that reason, we also call it as inductive or lagging load. And finally, for the capacitive loads, it is going to be less than 0. Okay, so this is for capacitive loads, or it can also be called as leading load. Since theta V will be less than theta I, that means the current phasor will always be leading the voltage phasor. So theta V minus theta I will be less than 0. So sine of theta V minus theta I will be less than 0, making the reactive power to be less than 0. So depending on the sign of the reactive power, you can decide whether it is an inductive load or a capacitive load, or if it is 0, then it is a purely resistive load. Okay. Now another point is, we have seen the impedance triangle. Similarly, we have a power triangle. Okay. So how will the power triangle be? P will be the base, the real part, Q will be the imaginary part, and S is going to be the hypotenuse. And the angle that we have here, this is nothing but the impedance angle. So that means you can take the impedance triangle as well, and here also theta will come, right? Here it will be R, X and Z. So the impedance triangle and the power triangle, they are both similar. That means the angle here will be same. All of the angles are going to be same. Whereas the size might be different. That means the length of each of the side, it might be different, but the angles are similar. So that's when we call them to be similar triangles. So you can say the phase of S is equal to phase of Z, which is equal to, you can either write as tan inverse Q by P or tan inverse X by R. Okay. So both of them will be equal, or you can write as equal to. Okay. So why it is coming like that, why the angle is equal, you can directly get from the expression, right? So what was the impedance phasor? V bar by I bar. So what is the angle you will get here? Angle Z is equal to angle of theta, angle of voltage, minus angle of the current. And what about S? S is going to be V bar I bar conjugate. Okay. So this is going to be, angle S will be angle theta V plus angle minus theta I, because we are using the conjugate. So that is why the angles of the phases of both impedance and the complex power will be the same. Finally, one last point is the apparent power. What is the difference between apparent power and complex power? This is a major doubt that many of you might have had if you have not read the proper textbook. Okay, so we call S is equal to P plus JQ. This is a complex number, right? It has a real and imaginary part, it has a magnitude and phase. Okay, so this is called as the complex power. Now, if you express S as the form of magnitude, then the magnitude of the complex power is called as the apparent power. So this is the magnitude of complex power, which is called as apparent power. So that is the difference. Complex power is a complex number, while apparent power is just a number. It is the magnitude of the complex power. So if you write in terms of the voltage, S is equal to V phasor into I conjugate. Okay, and apparent power mod S is equal to the mod of V RMS into I RMS. So why are we calling it the apparent power? So you can see that it is the product of the voltage and current. So this would have been the power that would have been delivered if the cos power factor is not present. Okay, so that is why it is called as the terminology we are using as apparent power. The power that is seeming to be delivered, but it is not actually delivered. Now, since there are various expressions of complex power in terms of the voltages, in terms of the real and reactive power, and we can even get in terms of the resistance impedance values. Okay, so we will make a list of all of the expressions, various expressions, so that all the expressions are in one place. Okay, so first expression is the main definition, that means from where it originated, V bar I bar conjugate. Okay, then what about in terms of the real and imaginary parts, we write as P plus JQ. Now another is in terms of the impedance. So V bar I bar you can write as V bar divided by Z conjugate. Okay, so what are you going to get? Mod V whole square divided by Z conjugate. Okay, so because a complex number into its conjugate will give you the square of the magnitude. So for this reason we can write as the complex power, you can write as mod V square by Z conjugate. Okay, then another expression is in terms of the current and impedance. So what will that be? S bar you can write as, now V bar you can replace with I bar into Z, and here you have I bar conjugate. So once again you are going to get the magnitude of I square into Z. Now we can get the same expression for P and Q as well in terms of the current. So if you can see, S bar is equal to mod I square Z, which you can write as mod I square R plus JX, right? So you are going to get mod I square R plus J mod I square X. But we know that the real part of S is P, so this must be P. P is equal to I square R, and the imaginary part of S is Q. So Q you can write as I square X. Okay, so therefore P is equal to, so we will write as RMS square into R, because remember we are using the RMS values here. If you are using the maximum values, then you will get a slightly different expression. Okay, so this Q is equal to I RMS square X. Okay, X is the reactance, where X is equal to reactance given by XL minus XC, inductive reactance minus the capacitive reactance. Now one more last simple point that we have regarding the AC power is conservation of AC power. So we know anyways that any power it will be conserved. Okay, So, but which power is going to be conserved? Is it the real power, the reactive power, the complex power, or the apparent power? Okay. So, the complex power P and the reactive power, these all will be conserved, but the apparent power is not going to be conserved. Okay. So, we will see why that is the case. If you consider a voltage source which is delivering to two impedances which are in parallel. This is Z1, Z2. Now, this is V bar, I bar. So, let us take this as I bar and I1 bar and I2 bar. So, what is the condition for conservation? The power that is delivered by the source should be equal to the power that is absorbed by the impedance. So, in this circuit here, the complex power delivered is given by S bar is equal to V bar I bar conjugate. Then what is the complex power absorbed by element Z1? This is given by S1 bar is equal to V bar I1 bar conjugate. By Z2 it is S2 bar is equal to V bar I2 bar conjugate. So, the total complex power that is absorbed is S1 bar plus S2 bar, which is going to be equal to V bar I1 bar conjugate plus V bar I2 bar conjugate. So, this you are going to get as V bar into I1 bar conjugate plus I2 bar conjugate. So, this is going to be the sum of these two, which is nothing going to be the conjugate of the total current I here from the KCL. Okay. So, you are going to get V bar into I bar conjugate. This is nothing but the complex power that is being delivered by the source. So, complex power is indeed being conserved. So, we can write in a generalized form S bar is equal to S1 bar plus S2 bar plus so on till Sn bar if there are n number of sources that are absorbing power. Now, from here you can each of the expressions you can write as P plus JQ is equal to P1 plus JQ1 plus P2 plus JQ2 plus so on. Now, what will happen? All of the real parts you can add, right? So, you are going to get P equivalent is equal to the sum of the real parts. So, this is also being conserved, the real power. What about Q? The addition of all the imaginary powers. So, Q1 is Q equivalent. So, Q1 plus Q2 plus so on till Qn. So, this is also being conserved, this is also being conserved. Whereas, if you take the case of apparent power, here you cannot write as mod S is not equal to the sum of the individual apparent powers. So, why is that the case? Because S will be root over P square plus Q square. S1 will be root over P1 square plus Q1 square. So, this is not equal to if you take two of the elements. So, this is not equal. These both are not equal. Okay. So, that is why the apparent power we cannot write as the sum of individual apparent powers.